Just a few slides to show you a new product coming out probably next month. A wider pore fused core particle from the Advanced Materials technology, and we sell the product as the Halo product. Just a real brief review of why these types of particles provide the kind of resolving power that they do, and that is primarily the much lower A term and C term for very dense particles that pack extremely well into the beds, very stable beds, and very uniform flow paths from the inlet to the bottom. The very shallow pores, only a half micron in depth, are all very uniform in depth. It gives you a flatter Van Deemter curve at higher linear velocity, so you have a lower curve and also a flatter curve. Here's an example of the distributions of the particle sizes. These are about 4 times, 5 times narrower than your typical totally porous packing material that's used in HPLC columns because of the way that they're made as a core, and then the outer layers are put on in stepwise fashion after the fact. An example trace showing the pore distribution of the peptide column compared to the standard 90 angstrom column. Apologize for the heterogeneity of the slide format, but I got some of the slides from the ISPPP just this morning, so I tried to shoehorn them in here. Some basic data on the fused core peptide particles. They're also 2.7 micron with a 1.7 micron core, the half micron porous shell that has the bonded phase primarily in it. Somewhere between 14 and 16 nanometers, 160 angstrom, 140 angstrom pore size. That varies with not being able to talk to the people who have produced the product most recently. Comparison of a small molecule Van Deemter compared to the 90 angstrom phase, with the peptide phase being slightly higher than the, slightly higher as far as the reduced plate height compared to the 90 angstrom phase. The difference for the 4,000 Dalton beta amyloid peptide, the 90 angstrom curve now is on the top. So you have your peptide trace here, your C branch of your Van Deemter curve out here. As far as column durability, here's a 2.1 by 100 Halo peptide C18, half a milliminute, 60 degrees C, an overlay of the runs from 1 to 775 for a variety of peptides ranging from a dipeptide all the way out to about 14 kilodaltons and 5,800 daltons. An example tryptic digest of apomyoglobin. This was done on an Agilent 1200 SL. 124 bars is maximum pressure for this. Peak capacity of about 212 there. And here's a comparison of the 90 angstrom Halo with the 160 angstrom peptide C18 compared with a 1.7 micron C18, probably from Waters, and then a 300 angstrom 3 micron column. You can see all the peak capacities are quite in the same range for these three column types, all 2.1 by 100, 45 degrees C. Comparison, now one of the advantages of having a 2.7 micron particle column is that you can, because the pressure is so much lower on this than it would be on a sub 2 micron particle, you can put 2 of them in tandem to get additional resolving power from that. Here's a couple of different peptide maps for apomyoglobin and also for transferrin. Comparison of some fast gradients done on a 2.1 by 50 peptide column, again at a half a milliminute, comparing several different temperatures for these very difficult to chromatograph, very lipophilic A beta peptides from Alzheimer plaques. And just to sum up, a new product coming out. We anticipate an improved version, not improved version, but another phase beyond this in maybe within 6 months that will deal with more proteomic type situations, LCMS. Allows fast gradient separations of peptides and small proteins. I'm guessing somewhere up in the 20 kilodalton top end for that pore size. Much narrower peak widths and excellent mass transfer, and certainly outdo the widths that you can get on a totally porous particle, and you can run these on conventional as well as on UHPLC and UPLC systems. And that's it.